Thank you so much, Marco. So this tool is, I'd like to think of it as not a database. It's a suite of analytics. It's essentially that interface with different objects that will help you analyze essentially genomic data. And these, I think there are, we call this Gen-TB, and Gen, stands for genomics of TB. And essentially we have 4 main features that we've designed in its current version, but we're planning on extending it in the future. So I'm going to do the brave thing of trying to do a little demo for you of the tool. So bear with me. So I'm sorry, this is kind of small, but so there are 4 main features, and I'm going to start off with this prediction feature. So if, you can click here or click here, and just so everybody knows, and if they want to follow me on their laptops, the URL is gentb.hms.harvard.edu. So if you click on predict, oh, no. Maybe not. Okay, so I'm going to try to go to Wi-Fi, actually. Oh, no, hold on. Not that one, this other one. Okay, sorry. Let me try to go to Wi-Fi. Okay, perfect. Okay, so what you see here is that you have the option to, okay. Oh, this won't work? No, okay, that's fine. Okay, perfect. Yeah, so so you can create a prediction from different kinds of input data. The first thing I'm going to start with is, just to demo this, you can input a parent FASTQ file, a whole genome sequence data. And it's fairly simple, so you just, say type a description. I'm just going to type test. And you pick a pipeline. Here we're picking the whole genome sequencing pipeline. And then you upload your FASTQ files from Dropbox. So I'm just going to demo here what that would look like. So I have a pair of some FASTQ files. So you can click more than one, as many as you want. And then you click choose. It'll immediately sort them into the forward read files and the reverse read files. And then you click submit. And then it'll essentially go through, put the data through the pipeline. The first bit that's doing here is the data upload. And then it's going to be mapping the reads, also going to do a quality control step, then going to call variants, annotate them, and then push the variants into the prediction tool. This, at the moment, the timeline to do this is about a little over an hour because we do mapping of all the reads. But the positive side effect of this is that you actually can then download all the variants for the whole genome. But in a future version, and it could easily actually do this, restrict the mapping to only the regions that are currently relevant for the prediction model, and that would obviously make it so much faster. So I'm just going to go back to predict here just to try a different kind of prediction. I'm going to try this option called manually entered mutations. And so here you can essentially pick your favorite mutation. So say you first of all pick the drug. So you click isoniazid. You have a list of the different drugs for which you can make a predictions from. So I'm just going to, for demonstration purposes, click CAT-G, and then I'm going to try to just pick a canonical mutation, S315T, and then you click add. You can also say add additional mutations for as many drugs as you want. So for rifamycin, you can click RPOB. And so forth. And then you can essentially submit this. Essentially what it's going to do, it's going to assume that The variants elsewhere have been tested and negative, so that's important that you take that into consideration. But it's going to essentially generate a prediction for you based on the mutation profile for your strain. And it'll take a few minutes to run, mostly because at the moment we're using the university's cluster. It takes a little bit of time to get the job sent. But well, I'll come back to it, and I'm just going to show you some results. So for example, actually I have it over here. So when you so I should just say that you can create an account that's completely free. When you create an account, the only thing it does, it allows you to store all the data results that you've input over time. So, and you can kind of go back to them under this My Datasets tab. I'm just going to, you might recall that in my previous talk, I showed you the series of strains obtained from the same patient over time, over the span of 10 years. And I just want to show you the results of our prediction model using whole genome sequence data from those strains that were obtained over time. And so you'll see here that, in fact, there is, this is the isonized column, so you get a heat map result. Each row represents a different strain. Each column represents a different drug. And the darker, the more red the square is, the higher the probability of resistance. If you want to essentially see what that probability is, you just hover over the square. So this tells you that the probability for this strain called Italian 10 of being isonized resistant is 0.719. It also gives you the false positive rate and the false negative rate for the prediction. And if you want to understand why it's predicted to be resistant, you can click and it'll give you essentially a mutation profile. At the moment, we classify these mutations into important and other. Important meaning that they were part of this most predictive variants that I obtained using the bootstrapping method that I showed you earlier. And other just means other. It doesn't mean it's, that these are neutral variants. That it just means we don't have a lot of information or enough information to know that they're important right now. And so you'll see this strain has a mutation in EMB497K. It has this other mutation in CAT-G and also has a promoter AHBC. So none of these are canonical variants, and none of them are very common. But it's so interesting, actually, that our model, remember that there were several step-ups that I showed you. We don't actually have the Italian 6 and 7, which were the intermediate, the kind of more intermediate, but it does, because of inability to extract DNA from those isolates. But the machine learning algorithm did actually predict nicely that there's at least 2 step-ups where they should be according to the phenotypic result. And even though there were no canonical mutations, the algorithm was taking interactions between these 3 mutations and essentially deducing that those are likely resistant. And so you can see that for the other drugs too, like this one has a S450L mutation, RPOB, and this is the same EMBB mutation that I showed you earlier. It also has PNCA mutation, and so forth. So you can navigate, and you can also download that data. So I'm just going to show you some other features. So we have also a mapping feature. I'm just going to refresh the screen. Just going to take a second. So this is essentially a feature that allows you, that's actually very nicely adapted to surveillance, where you can actually look at the distribution of phenotype and genotype by geographic region. So here I'm just clicking on the country Peru. It tells you the total number of strains that have been sampled and how many are resistant. When you click on it, it also gives you this little breakdown by drug, so you can magnify it, and you can also download the data. You can kind of switch between countries here. You can look at Canada. You can look at the US, and so forth. You can also look at the lineage distribution in each country. And we currently have a feature that allows you to search through different mutations. It's not perfect yet because it's been actually challenging to search through a very large database of mutations. We actually reached the limit of this kind of language that we're using. We're using R and actually a Java wrapper for R, so we've decided to switch to Python. And so we're actually now developing, in the last stages of developing the new version of the mapping. And this is how it's going to look like, but essentially allow you to drill down looking at mutation frequencies by mutation lineage, drug, and country. So we also have this third feature that allows you to essentially do simple point-and-click statistical analyses of the current data, and you can actually upload any data set that you want to do this, as long as you use this platform called Dataverse. It's integrated with it. And essentially what it does is, you could see on the left-hand side here, essentially a list of all the different variables that are present in that data set. So if you unclick or click, it kind of pops up as a little bubble. You can kind of move it around. It's kind of fun. And you can then, what you can do is if you hover over it, it gives you some summary statistics about what that variable is, how many are resistant to it. So this is ethambutol DST result, how frequently we saw resistant in 943, and I'm sorry, these are kind of small. Let me try to magnify this. Better, yeah. And so you'll see essentially how many have results and what are the frequencies. You can also get some, if you pick another variable like this ethambutol mutation variable. And then what you could do is you can designate one variable as a dependent variable, and then you could try to make one as a predictor. So if you right-click on the other variable, it puts out an arrow. And, sorry. Can be a little finicky with the laptop mouse. Let me just try to move it here. Oh, sorry. There we go. So then what you can do is there's a feature here on the right-hand side that allows you to run almost any kind of regression model using that data. So you can, here I'm going to pick logistic regression because the outcome variable, which is the drug sensitivity profile, is a binary variable. And then you can click, obviously this is a toy example because we only have one variable, but you can click as many variables as you want, and you can then click estimate. And it will give you essentially the p-value for the association of each variable with the drug resistance profile or whatever other dependent variable that you select, and what the estimate coefficient is. So, and the other feature of this, so this integrates with a data repository called Dataverse, and you can actually download all of the data that's on inside of this. You can also upload data if you want to play with it with Two Ravens, this Explore tool that I showed you. And I'm just going to try to go back now and see if I can, my manual prediction is now completed, and so you could see it is. So I had put in catchy SG15, and so you could see it kind of popping up here, but essentially this is sort of a proof of concept of how the algorithm works, and so forth. So essentially, you can make direct predictions from manually entered data, and that's it. So thank you.